to the ITC lunch. I just wanted to make a brief remark at the opening because last time we noticed, or at least some people told me, that there were some people, especially in the upper floor, that as soon as they finished their sandwich, left. And I would like to make a comment that this, as far as I'm concerned, I don't think it's polite towards the speakers. Coming here and having lunch with us is a commitment to stay for most of the lunch. So I very much hope that this will not happen very frequently. We just heard an excellent ITC colloquium by Feryal Ozel. And she will also tell us at the opening of this lunch about what the X-ray Surveyor, a future mission, will do for us. I guess this is time dependent, of course. With NASA missions, we cannot ever forecast what we might be looking for when they are launched. But at least we have some very good motivation for this Surveyor that Feryal, together with Alexei Viklinin, are leading. And then we'll hear from the colloquium speaker later this afternoon, Jim Peebles from Princeton, who will tell us why a flat galaxy phenomenon may be telling us something new. So that should be very interesting to hear. And then we'll hear from Victor Pankratius, who is visiting us from MIT, Haystack. He should be somewhere over there. And he will talk about computer-aided discovery, leveraging machine intelligence for scientific insight generation. So if any of you is worried about what may happen when you get to 70 and you don't have good ideas, computers will be here to help. Victor will tell us how. Finally, we'll hear from Dan Dorazio, who is a new fellow at the ITC, and he will talk about a lighthouse in the dust, reverberation of periodic emission from massive black hole binaries. Yeah.
Is this on now? Okay. All right, so I'm going to give a bit of an unusual lunch talk in that I'm not going to talk too much about science that we do today, but the science capabilities that we're hoping to have in the next decade. And I want to concentrate mostly on why you should care about an X-ray mission in the United States in the next decade. So as Avi mentioned, I'm chairing this study that NASA commissioned along with Alexei Viklinin, who's at the SAO here. And I'm presenting this on behalf of a quite large science and technology definition team, about 25 of us, in addition to the study offices, and about maybe 200 people who are on our science working groups, probably even more. So the concept of surveyors came out of the NASA 30-year roadmap, which I took part in. Basically, the equivalent of the great observatories, but for the next decade, we looked at what science still needs to be addressed and what capabilities are required to address those. And X-ray Surveyor, all of them were named Surveyors. We're in the process of renaming it, so stay tuned for our more exciting name, is basically identified as a necessary next decade mission in this astrophysics roadmap. And the idea behind these studies is that we provide a compelling and executable mission concept that is to be presented to the 2020 decadal along with these other three mission concept studies. So we already have a strawman mission concept. Obviously, we're working very hard on refining our science case and potentially adding or subtracting from these mission capabilities. But this was the result of the one-year study that Marshall Space Flight Center and SAO concluded at the end of last year. And the several things that should jump out at you is a huge leap in sensitivity compared to Chandra, and that is achieved by a combination of high angular resolution, so sub-arc second resolution, and a much larger effective area than Chandra currently has. So we're aiming for about 50 times more effective area and a really low threshold in flux in the 0.5 to 2 keV band. And combined with a large field of view and the subarc second imaging that keeps us from being confusion limited, this is going to provide a huge potential for surveys down to very low flux limits. So again, this is a straw man mission concept. This may not be exactly what we present to the decadal, but what could a mission like this do for the community in general? Not just for the X-ray astronomers, but for the astronomy community as a whole. So let me begin by reminding you, in fact, I chose the title, Matter in the Universe was a course that Bob Kirshner taught for many years here at Harvard. And I was a TA for it when I was a graduate student here. So now we know a lot about matter and energy in the universe. And we know that we have to work with very little in order to understand a lot. And very little means that about 4% are atoms, 0.5% are in stars, and of this 4% baryons, about half is in a hot gas phase, which means that if they emit, they are likely going to emit high energy, so X-rays. If we do only optical and infrared surveys, we are limiting ourselves to an incredibly thin slice of this already thin slice. So basically, what the X-ray surveyor is aiming at is getting a complete picture of the universe by looking at all its components that we can get a handle on and looking at the interplay between this hot gas and everything else on this pie chart. So given that that's our focus, what are some of our science drivers? What would such a mission be able to address? There are many. This is truly not an exhaustive list, and it's on purpose not an exhaustive list. But some key concepts that we may all care about are emergence of black holes in the early universe. We all know that the coevolution of black holes and galaxies played a huge role in shaping the galaxies that we're trying to detect at redshift 10. The nature of seeds is an open question, as I will get to. X-ray Surveyor can help us with that. Cycles of baryons in and out of galaxies. We know that about almost half are in a hot phase. And whether this is the circumgalactic matter or intracluster matter or matter truly in the filaments, this is something that we care about in structure formation. Feedback is a problem that keeps coming up again and again and again in many different contexts, whether we're talking about stellar feedback, supernova feedback, feedback from black holes in all settings, from our own galaxy to nearby galaxies and clusters to, again, our early universe. How did the star formation history get affected by feedback? Physics of accretion and compact objects, and obviously in this new era, X-ray counterparts of gravitational wave events and multi-wavelength phenomena is a science driver. So in one slide each, I'm going to touch on 4 topics. The survey capabilities for such a mission would be truly tremendous. So here, as an example, we're showing the limiting flux as a function of the survey area that can be achieved in a 15 megasecond program. Okay? So a mission like this would provide about 800 times higher survey speed than the Chandra Deep Field limit. And furthermore, because we will never be confusion limited, it would basically get down to the particle background, which is about 10 to the minus 19 ergs per second per square centimeter. So compare that to something like Athena, which our European counterparts are planning. It would truly provide a whole new realm that is not achievable without the angular resolution. So I said I'll just touch in one slide on several topics. In addition to finding all of the X-ray sources out there and being able to separate it out to its components, one of the main mission drivers is finding the supermassive black hole seeds. This is a slide that the gravitational wave community likes to show as a redshift and as a function of redshift and black hole mass. What is the sensitivity of the gravitational wave observatories compared to future electromagnetic probes. And this is the line that they draw, keeping something like Athena in mind. And these are some different evolutionary scenarios that they picked for this particular plot. And these are the contours of numbers that you can get down to. So, for example, at 10 to the 4 solar masses at redshift of 12, you can get down to so many numbers in gravitational waves. Well, with the X-ray surveyor, the landscape changes completely. This is what we are sensitive to. We can really get down to 10 to the 4 solar mass black hole seeds at redshift 10. And this is exactly the regime that we need in order to be able to identify or discriminate between the light mass scenarios and the heavy mass, heavy seeds scenarios. This is, and both of these are still viable, whether you start from very small masses and have a sequence of mergers, or have collapse of much more massive objects that provide the seed for accretion. This is really the regime that we're going to be able to probe. So why can we do this? This is a simulated image of what the X-ray surveyor would be able to see, all the point sources for a JWST field. So it's a 2 arc-minute by 2 arc-minute deep field. Again, this is the JWST simulation. And on that, these are the black hole seeds and X-ray sources that we will be able to see with the X-ray surveyor. If we had 5 arc-second resolution, this is the best that we would be able to do. So obviously, the combination of the sensitivity, the angular resolution with the large effective area is key here. So what I would like to say is that since we are spending a lot of resources on building not just JWST, but WFIRST and GMT, looking at these early galaxies, both from space and from ground, we really need the second part of the picture in X-rays. Cycles of baryons in and out of galaxies. Anybody who has worked on galaxy for, can I have one more minute? Okay. Anybody who's worked on galaxy formation knows that you need feedback and hot gas, whether you want to quench star formation or you want to get metals out of galaxies. Feedback and hot gas is your friend. Without it, you don't have galaxies that look anything like today's galaxies. So we know that there are cycles of baryons, that there must be cycles of baryons in and out of galaxies. And we are trying to detect this hot gas by reaching surface brightness levels that are 1/30th of what Chandra can reach. So this is a short simulation from Andrei Kratsov and collaborators. The scale is shown up there, and what this will show you is how a galaxy and its surrounding volume separates into 2 components that can be viewed very clearly in the temperature of around 100,000 degrees and temperatures that exceed it that can be viewed in emission in the X-rays. Okay, last one slide. For those of you who care about star formation and planets, it's becoming more and more clear that the early life of a star involves a lot of high energy emission, and this might play a huge role in how the protoplanetary disks behave. And in fact, X-ray flares might be the component driving MRI in the protoplanetary disks and allowing planets to form in the first place. And this is a short movie from Chandra of the Orion star cluster, and it's a time lapse of a long observation, and you see the flickering in the X-rays as well as a major flare from one of the young stars, about a solar mass star. And a lot of new simulations now started addressing how that high energy emission interacts with the protoplanetary disk. Okay, so I think I'm just going to leave it at that. Hopefully you will be supportive of a next generation X-ray mission to answer all of these questions. Thank you. That's a very good question. So what is driving the angular resolution here is precisely what we know about the nature of point sources and the extended sources and the ability to separate out those components. So we think that if we are able to achieve half an arc second resolution, we'll never be confusion limited. We'll only be background limited.
Very nice talk. My question is something outside of the talk, namely, where are we in the technology development to achieve these major gains relative to Chapter? What has been demonstrated?
Very fair question. So obviously, if we're going to go to 50 times the effective area of Chandra, we need lightweight mirrors. And there are 4 groups around the world that have been putting major effort into developing these lightweight but high angular resolution mirrors. The best that has been achieved so far are 2 millimeter thickness full shell mirrors. And this is a study that was done in Italy that did get to arc second resolutions. When we're talking about even thinner shells, for example, the ones that SAO has been working on, the Marshall Group has been working on, and Goddard has been working on, we haven't quite gotten to that angular resolution, but there is, so that's our highest priority in terms of technology development. When NASA asked for our input as far as prioritizing technology, we said lightweight optics is our highest priority. But at 2 millimeters, that's still, that was done for a 1 meter diameter. So we're getting there, I would say. And which of these will end up being the most fruitful direction, we don't know yet. And we don't have to choose at this point. We just need a realistic roadmap. Thank you.
Oh, no, it's on this end. So I come seeking your thoughts. Did I kill it? No, no. On an issue that has fascinated me, and others, of course. Is it there? This is all about images, so oh, there it is. So, first, to avoid misunderstanding, I do understand that you people, many of you here, are making fantastic advances in modeling galaxy formation, impressive advances that include quite realistic-looking galaxies. But yet, I have the feeling that there's something missing from these simulations. It's here illustrated, a galaxy seen kind of edge-on. You cast your eye across it. Can you see where the center is? There's perhaps a little bit of activity here that might be the center, but to a first approximation, I'm impressed by how flat this thing looks. As if it's all disk. Thin, thick, I don't care, but all disk. Here is another such galaxy, seen dead on, edge on. Maybe you see a little bulge of light here, a bit of a bulge in the center, but again, wow. Here is a deep image. It charms me that this was obtained by an amateur astronomer who has 2 great advantages over the professionals. First, he has a small telescope, so that one CCD field covers this galaxy. He doesn't have to worry about patching together pieces. And second, of course, he's his own tack, so he can observe as long as he wants. It is fascinating to me to notice that there's no progenitor seen. I thought this was unique until I learned today. Where are you? I learned that there's the same in the in the Milky Way, we observe that as time goes on, precession will cause this thing to fatten up, and it will eventually end up as a good approximation to a stellar halo. These stars show that galaxies do grow by merging. They also show that a merger event such as this is going to add to the stellar halo, surely not the disk. Is that fair? Oh, good. Here's a simulation, very successful. Others, of course, are in the market. But I point out a couple of things. I'm not even tall enough to reach, but yes. Perhaps you can see the blue lines. They are present positions of stars in the bulge. You can see the black line, that's initial positions, or perhaps it's the other way around, I don't remember. A simple rule. If you end up in that bulge, that's because you were formed there. If you were formed out here, you're not going to settle into that bulge with much probability, I would think. A keen rule. Of course, that bulge could have consisted of two earlier bulges that merged and would puff up somewhat. So we cannot say for sure that always stars in the bulge were born in that bulge, but I bet you they were born in sub-bulges that come together. Stars that formed in the halo surely formed before they fell into the galaxy. And stars that formed in the disk, here it is shown that the black line is the distance from the center of the galaxy on formation for disk stars. The blue dashed line, the position now, and of course they're very similar. This doesn't say whether the star formed in the plane or only formed close to the galaxy, but I think it's again a good bet. If you're in that plane rotationally supported, it's because you grew up there. So, here's why I think this is kind of funny. This is a pure dark matter simulation. It's old. I'm sure much better is known now. But I remind you of the rules of the game in this plot. This is called Aquarius. Comes out of Simon White's N-Body sweatshop. This is the nominal virial radius. All particles that are not in the virial radius at z equals 0 are not plotted in any of the earlier times. Stars that are within 3 kpc of the center are plotted in yellow, and the positions of the stars there labeled as yellow are shown at earlier times. Stars between 3 and 7 kpc, about where we are plotted in black. They look rarer than the stars plotted in yellow because yellow is plotted on top of black. That aside, we see that the stars that are now within our distance from the center were at a redshift 1 considerably spread out. Here is the scale, 300 kpc, and they were in fragments at redshift 3. This is a reminder on the right that at a redshift of 2 to 3, star formation rate density was an order of magnitude greater. Surely, therefore, stars may have been expected to have been formed in this galaxy. By the way, I should have mentioned that these are Milky Way mass type halos. Where would they be expected to form? Well, I suppose in the denser regions. You see the denser regions scattered about. It seems reasonable to suppose, if I didn't know about the structure of plane galaxies, that the stars would be forming and falling together and forming a stellar halo, but these stars are not going to form a stellar disk. This surely is not a very comforting picture for the formation of those flat galaxies I just showed you. Now you could ask, are flat galaxies common? Well, through the miracle of the web, well, I've already said this, I have collected from Brent Tully's catalog of galaxy distances within 10 megaparsecs and more luminous than 10 to the 10th solar luminosities in, I think it's K-band, all 38 galaxies. This subset has what I trust are carefully measured bulge to total luminosity ratios. Through the first two rows, bulge to total is essentially 0. In the next row, bulge to total climbs up to 0.1 at this point, and then gets to 0.1. And now we get some transitions. M81 has a bulge, M31 and Maffei has a real bulge, and Centaurus A. Here are the other ones. These have perhaps less secure bulge to total ratios, but they look kind of similar to me. In short, in our neighborhood, among these 38 large galaxies, luminosity greater than 10 to the 10th K band, pure disk phenomena is common. It requires that not many stars formed before the material fell onto the rotating disk, which seems to me not to be simply understood in this scenario. So I'm perfectly aware, and have been made more aware this morning, that being without gas, these simulations are not that realistic. Plasma fluid dynamics causes dislocations, but we notice that a star that forms up there is going to move thereafter as a dark matter particle. And I see no way it's going to form a disk. Instead, it's going to form a bulge or stellar halo. So my question to hear an amazingly large number of sophisticated, knowledgeable people, I ask you, is this not a serious challenge to standard galaxy formation theory? I await an answer. I've made no selection. These are Tully's distances within 10 megaparsecs. This is a fair sample of relative numbers of ellipticals and spirals. No selection. Now, of course, we are in a limited volume. 10 megaparsecs is really a tiny volume of the universe. But still, is that what you had in mind? I would avoid the word major because I think the point is much simpler. To form these pure disk galaxies, you may not have accretion, mergers, or whatever of material that contains appreciable numbers of stars. Because when any material falls in that contains stars, it's going to contribute stars to the bulge or stellar halo. We must have then pure cold flow, pure, near pure, diffuse baryon settling onto this disk. It requires, you see, that in here, remember the scale. There, the black circle is the scale of where we want to put the stars in the disk. Somewhere in here, there has to be a little concentration that formed into one of those lumps in which all the stars are forming, and that all the rest of this material is pure diffuse matter. You have to control star formation to one tiny region in this blob. It sounds to me like a tall order, but you have a comment.
I'm happy about it. So these particles are selected from a dark matter simulation, yes? So
This is pure dark matter. No selection, though. These are all.
orbits of those dark matter particles may have actually nothing to do with the orbits of the stars or the galaxies. And so you can actually test this. You can look at hydro simulations to see what fraction of the orbits of the stars could be represented by dark matter particles. And actually, it's a very tiny fraction, and it's not just all the particles within a certain volume.
Yes.
But actually, you have to start implementing other things. The other,
Well, wait, but let's stop right there. Indeed, the stars moving as dark matter particles are moving on very special orbits, which had to be set by dissipative settling to the disk. Right, okay.
so then the other point is that actually, if you look at all those bodies particles you're selecting by doing that selection have given equal weight. So no matter what halo that particle came from, you're assigning an equal weight to the stars from that halo. But in fact, we do know that the stellar mass-halo mass ratio changes dramatically with halo mass, and so this should not be weighted.
That's a good point. But still, my basic question, how did you get all of the stars to settle into a disk?
Well, maybe we should talk about that.
Perhaps we should.
So Jim, I'm reminded in this election that all politics is local,
Yes,
that it has global consequences. Similarly, star formation is basically a local process.
it is.
And there is no predictive theory of how that proceeds.
You are right.
Should I give a damn? It seems to me that this is a clue to star formation. But it has nothing to do with what's going on in those pictures. If I may.
Oh, well, I think we have to pay attention to the picture. This can't be totally wrong in lambda CDM. But you mentioned locality, and one thought that I've been toying with, but should do more about, is we know that sub-ionizing UV radiation can destroy molecular hydrogen. And when you destroy molecular hydrogen, you really suppress star formation. So I could well imagine that somewhere up in here there was an accident that produced one humongous generator of sub-ionizing UV. That object will not allow stars to form anywhere else, maybe, except around it, where it's self-shielded. And that would be the center of growth coming down to here. Something has to select a point around which you're going to start forming the disk out of this rather broad spread of material. Sorry? Well, an AGN, yes, an AGN would be, and perhaps that AGN even is a good source of sub-ionizing UV.
I mean, another way of phrasing this problem is that the Milky Way disk has a lot of old stars.
Yes,
So we know that there was a disk in place at early times,
yes,
and yet there was a subsequent bombardment phase, which seems to not have destroyed the disk.
yes.
So that's another way.
And not only did it not destroy the disk, but it didn't build up a significant halo. Well, we have, what, 3 or 4% in the halo? Didn't build up a significant bulge. Again, the Milky Way is said not to have a bulge. But it certainly has a bar, yeah. Good.
But we are seeing the Magellanic Clouds in their first passage, so
Now,
we're
what...
getting bombarded.
Yes, but I'm not. Of course, there is a separate question: do you destroy a disk? But that's not the question here. It is, do you make a disk without making a bulge?
Any other comments? Yes, over there.
I just wanted to point out from the other aspect, looking at the observations, the sample that you picked, so it looked by eye like the cases where the bulge to disk ratio is larger, those look like more perturbed systems.
Yes,
And so
fair
with
enough.
Some kind of merger event, this can also increase the velocity, the velocity dispersion of the stars, which then can pop up the bulge.
It's an excellent point. So we can well imagine a merger event did something bad to M81 or to M31. Easy to imagine building a bulge, but destroying a bulge. Well, of course, if you could manage to make the bulge fill into the central massive black hole, you destroy the evidence, but that doesn't seem very promising. Yes, mergers have got to work for this. We have mergers, but as in that example of the ultra-thin disk I showed, I don't see that the mergers are doing much. Of course, building that stellar halo, but then the stellar halo is a subdominant component.
Thank you very much for proposing such a challenge to us.
Homework.
Test. Hello. Well, thanks for having me. And I'd like to use the discussion that we just had as a motivation for computer-aided discovery. So if you just think about what we just did, we saw some hypotheses of real, or we looked at real phenomena, created hypotheses, but then we started discussing alternative models and variants of models. What could it be that explains reality? And I'm a computer scientist interested in interdisciplinary science, and we're trying to advance exactly this kind of question by using artificial intelligence and cloud scalable approaches, because we want to be able to do this kind of thing on big data. Even though that's an undefined thing, big data, think of it like petabytes, exabytes, or even zettabytes, something really big. So we need to also scale the insight generation process. Okay? So I want to show you some examples today of what we've been up to and some basic principles that we have developed. But then I want to spend most of the time showing you examples where this actually works in practice. We've been very successful applying this to geoscience case studies, and we're now about to move into astronomy. And then I hope to get feedback from you here in the audience what other interesting things there might be to explore. So one thing that we want to do differently than the current data mining is we want to infuse physics knowledge and pragmatics into the search. So other than just using an algorithm that comes back and tells you there might be some interesting pixel features in an image or some interesting parts of a time series that you might want to look at, you want to have something that comes back and tells you this is a new physical phenomenon that contradicts a theory or that confirms a hypothesis that you've long had or an invariant. And we've been working on this following a model-based approach. So these models can be constructed from two sides. On the one hand, you can do things starting from the empirical side where you manipulate empirical data in different ways such that you can better highlight novel phenomena. But then from the theory side, you also want to construct some kind of models that you can vary such that you have templates in your search. Okay? So think of this, for example, in this context where you have a model, and imagine you have like sliders, like two sliders in this model. And depending on how you set these sliders, you get different shapes. In this case, it models tongues of ionizations to look for in the ionosphere. And the actual thing you might want to find is something like this here in a real instrument. And this exemplifies that if you were to use just some data mining that knows nothing about the physics, maybe you would get these pixels over here, and it tells you, oh, the gradient here is different than in the surroundings. But that's not really helpful. And the other thing you want to avoid is having many false positives that you have to go through, because if you scale this up to big data, you have like billions and billions of false positives you have to filter out. So we want to make the search more intelligent. And on top of that, we want to have human feedback in the search. So think of this like a big chess game. You're making a decision on how you process your empirical data. You're building up a workflow pipeline, but you have choices. You can choose different algorithms, different parameter ranges to actually highlight the thing you're looking for. And then from the theory side, you have different model variants that you want to test out automatically. But now in the search, you might not have an exact match, right? So that's where you can ask either for human feedback or use machine learning to determine that certain choices along the way haven't led anywhere. So in this big search tree, like in this kind of chess game, you can intelligently prune part of the search space, okay? And the search space can be spanned by algorithmic choice, by parameters, or even different model choices. Another thing that you can do with AI is perturb your models. So you start with a seed model that you think describes reality, but then AI can perturb it in ways that you might have not thought of before or that might be non-intuitive, and look for those matches. So that's where computers can actually help, slightly change the physics knowledge that you have in this model and try to find a match. And I want to visualize for the same data set that the choice of workflow is really critical. So what you see here is the same raw data of ionospheric total electron content processed with different workflows. So depending on what you choose, what kind of filters you choose, what kind of parameters, you might end up with something highlighting large-scale features over here, or smaller-scale features, or even nothing, which is pretty often the case. And this image here, by the way, led to a discovery of a tongue of ionization. So that's a real thing that has been detected in the past. Very similarly, this can be applied to astronomical contexts. So many of the principal component decompositions depend on the algorithmic choice. And there you have to make choices mostly intuitively these days. But we want an algorithmic approach. So the developed system that we have so far works in the cloud and accesses data from NASA. It has mostly time series and satellite data access. And what it does is apply this concept where you can have like different models generated by the system. And one output that you're getting is a heat map telling you which models produce similar results. Okay, so here, for example, you might choose one representative of a certain cluster of these models and then see if that representative is a valid explanation for a real phenomenon. And this is very abstract, so I want to show you very specific examples where we made new discoveries that have been also peer-reviewed and confirmed. So you've seen the ionospheric features. We've been very successful in geoscience time series. So what you see here is a volcano in Alaska, and there's GPS sensors all over this volcano, which record movements in 3 spatial directions. Now from these time series, you can do a transform to see like inflation and deflation events over time. Now the problem with this is that you have to choose a time window and different filters to actually see long-term or short-term inflation events. And it turns out we've been looking at a database worth 10 years of data in the past that's just been sitting out there. Volcanologists have chewed on it, and we still have found a new inflation phenomenon on this particular volcano. And this was thanks to the artificial intelligence that pointed us to a non-intuitive set of parameters that when configured and used in this workflow and in this model to find the inflation event, actually confirmed a new thing. And I'm very happy about this one because we said, well, why don't you write this up and send it to a volcanology journal, to have it reviewed by experts. And they came back and said, yeah, indeed, you found something new. And on top of that, we can vary different models, like different inversion models, to see like where the magma source chamber could be and how it's formed. So that's one particular successful study.
Could we just see?
Sure.
This is the volcano.
This would be the volcano.
Those arrows.
These would be GPS stations on the volcano. And that would be a principal component analysis applied to the time series, which kind of gives you an idea of how the forces are at that particular location. And there might be different models, like producing different arrows, depending on the kind of source model that you're choosing. Like MOGI, for example, assumes a spherical source. Okay, but you can also have silt sources or other kinds of models. And most of them are underdetermined, so therefore you might have different variants to choose from that might describe the same real thing. And that's the power of this approach, because these would be the variants to choose from. And then you can say, okay, so if I choose one of these variants, and that is a good enough explanation, then I don't need to choose all the other ones in these colors, because they would all be similar. So this is like an approach where we keep the human in the loop, but we give a more powerful way of scaling this discovery search. In a very similar fashion, we're looking at groundwater phenomena, and we can scale this out to continental scales all across the US to basically see how groundwater is depleting. You can measure that subsidence effects with GPS. We've applied this to planetary landing site selection. Here the idea is that you go to another planet or an asteroid. You may or may not have enough time to figure out where you want to land, because that's a complex problem. You have to take into account technical constraints like orbital mechanics, the constraints of your lander, delta t's, delta slopes, but then also the science that you want to do. And then you end up with a bunch of models. So what you want to have is like probabilities where you want to land. So I just scroll through the following slides. So we're looking at solar phenomena as well, but also planetary light curves. So here, to generate models of complex planetary systems, we're using actually a simulation. In this case, we're generating a light curve for a star with 2 planets. This is very simple, but we can add atmospheric effects and moons, and something that leads to very non-intuitive light curves. And then we can use those as a template to search for phenomena like these in the real data. And we believe this is more powerful than just trying to fit curves into, say, Kepler data and then trying to interpret. If you see these many bumps and maybe some other curvature, then try to interpret what it could be. This links you directly into the physics because you've actually designed a system that you hypothesized to exist. So ongoing work right now is to transfer these successes we had so far into time domain astronomy. And I think light curves are very interesting, but pulsars are also very, very fruitful as an area of study because you have lots of interesting effects. You have drift bands, which depend on the kind of model that you're fitting on the empirical data. The model-based approach also allows you to extract very faint signals, which otherwise would be very difficult to get out of the raw data. So we're kind of following a compressed sensing approach, if you want. It's the same idea where the information that you don't have from the empirical data is complemented through a theory assumption that you're making. And that can be multiple variants, so then you want to scale the search and this matching with the system, and that's exactly what we do. In a similar fashion, variable stars and stellar flares, I think these are all really, really interesting events and interesting case studies with lots of data and lots of potential explanations. And just to finish this up, what we're building not only scales to work on the cloud, you can access that from your laptop, you can even access that from the phone. So now you can do real big data analysis from your phone. And just think about this, going to Africa where most people have phones rather than laptops or PCs, they will now have access to big data discovery science. So thank you very much. I'm very happy to take more questions. The luck, what?
Attachment to a model.
Yes.
Or an ego that someone that developed the model. So if you design an algorithm, it can be closer to computers to design with life.
Yeah, the idea is the human specifies possible ranges of things that might be expected. But as you say, the computer just tries things out. And that was exactly the advantage that we had when we had this discovery in volcanology. Because some things are very unlikely and non-intuitive. So people think, why should I even try out this window size? It doesn't make any sense. I wouldn't expect to see anything. But the computer doesn't have, that kind of presumption. So you can optimize the way you're looking through the search space of choices and make it very, very efficient.
Since you're around, I suggest that people approach you after it's getting late and we need to move on to the next.
Thank you.
Okay, I'm going to, I guess we need a microphone. But I'm going to tell you about a recent result that I'm about to submit. So, one more moment. Is that good? Okay. So, to start, to give you a little preview and to explain the title, I just have a picture here, a classic cartoon schematic of the components of an active galactic nucleus. And specifically, I want to focus here on the accreting black hole and this obscuring torus of dust. And specifically the idea that the bright continuum emission from accretion on the black hole can heat this dust and cause it to emit an infrared, which we observe. And so today I'm going to use some clip art to replace the black hole with a binary black hole and ask what would the infrared emission look like if you have a periodically modulated continuum emission, and the Lighthouse part will come in later. So, all right, so just for some context, we're talking about massive black hole binaries at the centers of galaxies, which we don't know much about the population at close separations, but we know they should be there from evidence from galactic mergers and dynamical friction. And they're very interesting because if they do eventually merge due to gravitational radiation losses, we should detect that with upcoming instruments like LISA or presently the pulsar timing arrays. And characterizing a population of these binaries can teach us about the mutual evolution and buildup of galaxies and black holes. So how do we find them? Well, there's a range of different methods to find evidence for these objects over different ranges of the separation of the black holes, from gravitational waves to direct imaging of dual AGN on the kiloparsec scale. But right now I'm going to focus on this guy here, and the idea is to look at quasars and AGN and look for periodic continuum emission as some evidence for there being a binary there. So what would cause periodic continuum? Why would a binary cause periodic continuum variability? So there's a number of different ways, but one good way is if you have gas around the binary and it can accrete gas. And so myself and others have run simulations of this process, and we find that accretion onto a binary can be at the same level as accretion onto a black hole, sometimes a single black hole, sometimes exceeding that rate, so they can be bright. And they can also distinctly modulate the accretion rate, and so modulate the continuum emission. And so these are just some simulations I've done in the past. So periodic accretion can cause this type of modulation. Also, even if there is steady accretion onto the binary, which we do find sometimes, for example, a very small secondary black hole compared to the primary, you can get steady accretion. But even in this case, for close enough binary separations, the orbital velocity is relativistic, a few percent to tens percent of the speed of light. And so from special relativity alone, a very fast object moving towards you looks brighter, moving away from you looks dimmer. This is the relativistic Doppler effect. And so with this cartoon, I wanted to just point out that this depends not only on the velocity of the object, how much brighter or dimmer it looks, but also on its spectrum. And so here, for example, we're observing this binary, and all the light is coming from this guy that's going in orbit, the smaller guy. So as it's moving transverse to us, we see that it has this spectrum here, and we observe it in some band, and we measure its flux. As it moves towards us, it looks brighter simply from relativistic aberration and time dilation, but also from the Doppler boost, which now blue shifts the spectrum, and we see more flux in the V-band, and so the opposite as it moves away from us. So these are two ways you can get periodic emission from a binary. All right, so we use just this idea, and let me just say that it's nice that it depends on the slope of the spectrum, because it's something you can measure and then predict what the magnitude of flux should be in different wave bands. And this is something I've done recently with Zoltan Hyman, my advisor, to advance an interpretation for a periodically varying quasar PG1302 as the result of just this phenomenon, where you have a binary where emission, most of the emission is coming from the smaller guy, which is moving at 0.7% the speed of light and causing modulation, which you can see here. Black is the optical from the Catalina Real-Time Transient Survey and linear, and also measuring the different spectral indices, we can predict what the magnitude of modulation due to Doppler should be in the UV. And so far, this interpretation fits the data, but of course, what can we do to confirm this picture or to rule it out? One thing we can do is, of course, wait. And so these dates are for a recently submitted HST proposal to look for more UV, to measure UV spectra and continuum, and just beat down and see if this signal is really periodic. But the purpose of the talk today is to talk about other ways that we can confirm this picture. And so what I want to mention now is how I started. What would we expect the infrared emission from a source like this to look like? So the UV and optical reaches us, and we see this modulation, but it should also heat up the surrounding dust torus that I mentioned in the beginning. And what would that look like? Well, recently, people looked through the WISE catalog at what the infrared data looks like for PG 1302. And a nice kind of result is that the data available, so these are the WISE bands, this is the optical that you just saw, and these are the infrared, is that the infrared data points are consistent with having the same period of modulation, but with smaller amplitude of modulation and a phase lag, if you can see that here. Since there seems to be I haven't seen any models on what you would expect for the reverberated continuum emission, a reverberated periodic emission, I would put together some models to try and explain this data in terms of a binary. So let me just quickly tell you the salient features of that model. We assume that there is a dust torus centered on this periodic source, which is the massive black hole binary. And we assume for now, for simplicity, that all the UV and optical continuum from accretion is absorbed by the dust. And that dust is heated. It emits an infrared, and then the infrared goes to us. So we've just assumed that the dust is optically thick to the UV optical and optically thin to IR. And then we integrate that black body emission over the geometry of the dust. And crucially, you have to take into account that this dust region is parsecs across. So you have to take into account finite light travel time effects. So for example, the emission that you see from the front of the shell is from a different time in the source lifetime than the emission from the back and other parts. So you have to integrate over all of this. And we further look at two different types of sources. One that might be associated with varying accretion, which I mentioned in the beginning, where you have spatially isotropic emission, which varies in time, and one due to the Doppler boost where you have spatially anisotropic emission, hence the lighthouse. You're illuminating this dust as the binary sweeps around. And in both of those models, we input a period of modulation, and then also some parameters of the dust, also a binary inclination, and this dust torus opening angle and inclination to the line of sight. And from that, we can predict infrared light curves, and specifically the relative amplitude and phase of these light curves given the initial UV optical. And so what's nice is that in the limit that you integrate over all of the infrared frequencies, you get analytic results. And these analytic results teach us a good deal. So for the isotropic case, well, most importantly, let me point out that, so let's look at the relative infrared amplitude first. It depends, most importantly, on this ratio that I've written here of the light travel time across the sphere to the period at which the UV is modulated. And as a function of that, you can look at what type of amplitude IR you would expect to get. For this isotropic case in black, you find that as the size of the dust sphere gets very small and light travel time effects don't matter anymore, you recover the full variability of the UV just because light travel time no longer matters. And you're absorbing all the UV and just reprocessing in IR. But as you increase this parameter, you create a larger and larger light travel time across the dust sphere. Your infrared amplitude modulation decreases and goes to zero, as you expect for an infinitely large sphere. This modulation is washed out. And you also find some interesting features that there are zeros along the way, and these correspond to where the light crossing time is an integer number of periods of modulation. So this is, again, for a simple case of a dust sphere and sinusoidal periodicity. In the Doppler case, we find a similar result, but we find that as you go to a very small dust sphere, you have no modulation. And this is simply because this assumes that there's steady accretion. And if you integrate over a sphere surrounding a steadily accreting object, you'll find no variability. The only variability you see is because an observer has a line of sight velocity that's changing. So just from this simple analysis, you can start to try and differentiate between these two models and also learn about the size of the dust region. And I can also say that another interesting result is that as you would expect, you find a phase lag, which is of order the light travel time to the sphere in the isotropic case, but this has an additional 1/4 cycle change in the case of a Doppler source. And this is simply because what the dust sees is, so if you imagine the binary is moving towards the dust and it's bright over here and we're here, we see a different phase of the light curve as the dust does. So there's a 1/4 cycle change. And for example, we also have analytic results for many different types of tori inclinations, and you can start to use this to learn more about these features. So just a quick summary of that analysis. As I told you, you can predict the relative IR to UV optical variability and the phase lag. What also is interesting that comes out of this, in the case of a Doppler boosted emission, you can see no UV optical variation because the binary is face on to you, so there's no line of sight relative velocity. But the dust still sees a changing flux at certain parts, so you can have orphan IR variability, which would be an interesting way to look for binaries that we might have missed in optical searches. Maybe one of the more interesting things, which I'm not going to touch on now, but in future talks, is that if you apply this to the data for PG1302, so far we find a consistent model which consists of a thin aspect ratio 0.1 dusty disk at between 1 to 4 parsec, although we can't yet use that to differentiate between whether the source is isotropically varying or Doppler boosted. And of course, it would be interesting to apply this to the now growing population of these types of periodically variable massive black hole binaries. And here they are. I'll just leave you with that. So this is future work that we plan to do, is apply these types of IR models to the existing periodic candidates. All right, thanks. Mm-hmm. So you mean the changing position of the binary? Yeah, in this case, the dust is at the parsec scale, and the binary separation is 100th of a parsec of order. So, but perhaps if you were to think about the same process with broadline regions, which are much closer to the binary. Thanks.
You have a physical size of the inner torus.
I do.
It's around a light year.
Yeah.
Yeah. Was that anticipated by models for tori and their...
So this, gives us a number.
It gives
this
you a
idea.
number, which you can compare to theoretical ideas.
And so the theoretical input I have on this is, one, there's a sublimation radius.
Yes.
So it's outside of that, just barely. And two, I think studies of other galaxies have tried to do high-resolution imaging in combination with spectral energy distribution modeling. And they find that it should be smaller than a few parsecs. Because when they look in high-resolution imaging, they don't see the dust out there.
Yeah.
So
Would this be the inner radius of the torus or the outer radius?
I would say it's the inner radius in this case. Only
Good stuff.
it is.
I mean, you have actual data, though,
which has
really
been exciting. So I've been working on this for a few years, and only in the last 1 or 2 have we had actual data.
I've been wondering, I wondered often about believability of theories of galaxy formation. One of them is, where are all the binaries?
Yeah.
But you're telling us that they might be there, but at separations that don't hit the resonance, it makes this nice sinusoidal